Hello everyone. This week we will be considering the p-type controller. We are transitioning into controller design now. And we have a third order system given, which has a pole at the origin, S, and it has two poles at one of them is at -5 and the other one is at -8. And we have several questions here. First of all, we are asked to design a p-type controller such that the closed loop has a settling time of ts equals 4 seconds. Now keep in mind that the p-type controller is the most basic controller that we can come up with. It is a static coefficient, and we've talked about the root locus plot last week, so this is kind of the controller that we are considering here. And we had a feedback loop, a unit feedback loop, where the system, a certain coefficient, here is the coefficient, here's the system, and then we have the unit feedback. So keep that in mind that we are looking for a coefficient that will satisfy certain specifications. In our case today, we will have the settling time here, and also maybe the critical damped step response is going to be the aim. Now the settling time here, we need to talk about the settling time a little bit. But basically what we are trying to do is we have an open loop system and we can apply step to it, step type inputs, and we observe the output. Now we are not happy or satisfied with the settling time, which is basically the 2% band and the time instant where we're entering kind of this settling down of the response. Now we have GS, we apply step to it, and as you might remember, if you apply step to a transfer function, since this has some dynamics, it'll take a little bit time, the transients part, in order to settle or reach the steady state, sort of. So the amount of time that is needed to transition from the transients to the steady state is sort of a measurement of setting time. And we will have a controller, a closed loop transfer function, and if we apply step to this structure here, we want to have a certain settling time assigned to it. So the overall transients should satisfy a certain settling time. So that's our aim. Now, of course, we've talked about the unit feedback loop here, which actually was considering the poles of the closed loop. So we have a tool called the root locus plot in order to vary this coefficient k and see what the poles are doing. But these poles don't transition into transient measurements like settling time, overshoot, rise time, peak time, etc. So it has no direct connection to applying a step input and observing the output. Therefore, we need also to make that connection. So even though we have a third order system, we actually know that, for example, a first order system that looks like maybe this here, so a very basic one, 1 divided by s plus 1. So this system has 4 seconds of a settling time. We know that for a fact, since we can use the inverse Laplace transform, apply it to this. So let's assume that we have symbolic s, we have GSS, which looks like this, and then we can look for the input-output relation in the Laplace domain. Since we are applying a step-type input, we have 1 divided by s as an input, so this would result in 1 divided by s squared plus s, and if we take the I-Laplace, the inverse Laplace transform of ys, we will get basically the time domain representation of the response. So if we run it, hopefully we'll get a response soon. There we go, 1 minus e to the power of minus t. Since the pole is 1, everything is 1, there are not that many coefficients. And if you think about this response, if we plug in t equals 0, then e0 should be should be equal to 1, and this whole thing here should be equal to 0. As t tends to infinity, you will see that this term vanishes and we get 1 eventually. And between 0 and infinity, of course, there will be some transients, and we will have some values that are less than 1, and certainly at some point of time we will have exactly 1 here. So 0 here and 1 here. So the exponential here, if I plug in -1 to it, you can see that it rises from 0 to 0.36 in just 1 second. If we have another second, if we add another second, you will see, if we have 0, it drops down to that. So let me start over. We have 0, we have -1, it drops down quite a bit. And if we have another second, we have 0.13. It's almost it's tending to 0, and we can see here, approximately here, but it needs a little bit more time, we will have almost nothing left. So we are looking for, or we are aiming for, the time where this is basically 0.02, not 0.04, because we will have a 2% band and we will be happy with that. So if it's not wiggling more than 2%, then we say it's settled down, we don't have to wait further. So if we have 3.9, for example, you can see we are hitting that target, and approximately 4 works also, but it's kind of 3.9. But yeah, you get the idea. Actually, 3.91 should be the exact value that we should use, because it is exactly 0.02. So 3.91. So what happens? So and basically, if we have 1 minus 3.91, we reach the 0.98 band. And I can assure you that this will not overshoot, because this will not get bigger than 1, because at maximum you can have 1. This is an exponential term. So there will be no overshoot. This is a first order system, and I can see that in approximately 3.91 seconds this system will settle down and reach the steady state sort of behavior. So what happens if we have a different pole? Let's say let's have 2 instead of that, and let's repeat this exercise here. We can see that it is twice the amount of time, but this time around what we will do is we will say 2 times t should be 3.91, because eventually what I want to see here is minus 3.91, because that term will give us 0.02, and then we will have 0.98. So if I have 2t, it would be half the time. So it would be twice faster. So it means that divided by 2 should be the time instant that I should be looking for. So it will take approximately 2 seconds, but let's say 1.96 seconds to settle down for this system. And you get the idea. The basic formulation here is therefore 3.91 divided by the pole, because we have just a first order system. It has 1 pole only, and yeah, it depends on this. The generic solution would be p times t, and I would be always looking for 3.91. Therefore, t should be equal to 3.91 divided by p. So that's it. For first order system, this is quite obvious. And I can also show you that that would be the case. I define p, and there we go. Minus pt equal 3.91, and we get 3.91 divided by p. Sometimes we use 4 divided by because it's more easy to remember. 3.91, it's not that big of a deal, so we can use that. So we know that this system, a first order system, should always have a real root, because it has just one root. It cannot be complex. We're dealing with real coefficients in terms of polynomials. Therefore, the root should be real. And we also know that, therefore, there will be no overshoot. We need some complex parts, imaginary parts, in order to have overshoot, because otherwise we get just exponential terms in the inverse Laplace transform. But if we have some imaginary values, then we will get sines and cosines. So that would mean that if we have a sine, that means frequency and that means oscillation, so we have overshoot. For that reason, we know that these type of systems, first order systems, do not overshoot. Overshoot is 0. They have a settling time 3.91 divided by the absolute value of pole. If it's a stable one, it should be on the left half plane. And that's it. We also know the peak time, rise time, but they are not really that important or relevant at this point because it is a first order system. It is an exponential term. And yeah, the settling time is relevant, but the other one, of course, we have formulations for them, but for now, not really important. What about second order systems? Because this is only a real pole system with order 1. But what happens if we have a second order system? Now at that point, we introduce a notation which looks like the following, and it has its reasons. It's not arbitrary. So omega n squared, this would be our representation. And the reason behind that is the following. It deals with a second order polynomial, and we can look at the polynomial and determine whether it will have only real roots distinct or real roots coincident, or if they will have a complex pair as a solution. So based on that, the behavior of the system will change. And if you think about two distinct poles, let's say this times, let's say 2, then you would actually conclude, or you can conclude that these are just two systems connected in series. And if we have a certain value here, let's say step input, so 1. If this one doesn't overshoot, and in this case it is just maximum equal to 1, then let's change that to this, so we don't we get the gain 1 here. So if this one doesn't overshoot, it will be at max the input itself, because gain is 1. And if this one doesn't overshoot as well, then we will still get 1. So if we have real roots, what really happens is that we will have just connected first order transfer functions to each other in series. So therefore we would just conclude that, of course, this will not overshoot, and we can see that. But in the case of complex conjugate pairs, this is not really the outcome. We will have oscillations and overshoot. So therefore, we have this nice second order polynomial, and let's look at the discriminant delta b squared minus 4 times a times c. And since a is equal to 1, let's drop that. Since b is basically this one here without the s term, so let's take the square of this. And 4 times c is omega n squared. Let's take that too. And there we go. Now, if we work our way a little bit more, we'll see that this will become 4 times zeta squared times omega n squared, I guess. Yeah. And we have common terms, the 4, the omega n squared. So what we can do is we can just go ahead and factor it out. We will have omega m, we will have zeta actually. So omega n, zeta squared minus 1, and this will vanish. So this is kind of the thing. Now we will use the square root of delta. Therefore, it would become the square root of this term. And 4n squared, omega n squared, is going to be 2 times omega n times the square root of zeta squared minus 1. Now, if zeta squared minus 1 is positive, we can immediately see that zeta squared will be greater than 1, and zeta will be greater than 1, because by definition these two are positive values. So I can directly conclude this. By definition, zeta and omega n should be positive, and we'll see why. If it's exactly equal to 0, we will have zeta equals 1, which is called critically damped. So this is overdamped. And of course we will have also zeta less than 1, which is underdamped. There we go. Now in this case we will have complex conjugate pairs. In this case we will have identical poles and real poles. In this case we will have real poles. These two will not overshoot because they have real roots, and therefore overshoot will be 0. Here we will have some overshoot, and we will see how to determine that. And yeah, that's basically it. That's what we need to know here. The whole solution of this is of course equal to minus 2 times zeta omega n plus or minus square root of this, or square root delta, divided by 2a. A is equal to 1, so divided by 2, these coefficients vanish, and we can see that we have the solution here. Now what happens if we have this overdamped solution? First of all, well, we will have a root which looks like this, minus this, or plus this. So that's basically for overdamped. So let's place it there. If zeta is equal to 1, you can see that the square root vanishes, and we'll get this solution for the critical damped. Now, if zeta is less than 1, you can see that this here becomes negative. Therefore, I'm going to multiply everything with minus 1 and place a square root of minus 1 here. So this will actually give us square root of minus 1, which is basically I, and this is also I. So we have minus zeta omega n plus minus omega n times square root of 1 minus zeta squared times I. So this becomes the imaginary part, this becomes the real part of our poles. So we can directly see that. Now, if we have a negative sign here, and if these are the poles of the system, zeta times omega n should be positive in order to have a left half conjugate pair, left half plane conjugate pair. So this multiplication at least should be positive. And yeah, since zeta is a positive by definition, omega n is also positive by definition, the multiplication is positive, so it will be a stable pole pair. Now omega n is called the natural frequency, zeta is the damping ratio, because we can determine based on zeta if it's overdamped, underdamped, critical damped. And omega n is just the frequency, and the reason for that is lies in the solution. You should take the inverse Laplace transform. It has the whole in time domain representation, and you can see that zeta omega n will be there, and omega n will be the frequency of the sign that will be the solution. So you can look at the textbooks for more detail. I'm going to skip this part because this is basically just a reminder for you. Now, by the way, since this is on a complex plane, since we are in the S domain, and our polynomial depends on S, we can further analyze the solution in case of a complex conjugate pair, and we can, for example, look at the absolute value and see what really is the absolute value of this. Now, if you know the complex numbers, you know that if you're looking for the absolute value of this, of a complex number, all you do is go to the real part, take the square, and add the square of the imaginary part to it. So this would be it probably, and take the whole square root, which I'm going to do when I'm finished with this. So zeta squared omega n squared, let's have that, plus omega n squared times 1 minus zeta, so squared. And the whole square root of this. Now, let's basically get rid of the parentheses. So that would be it, I guess. Now you can see that we have zeta squared, omega n squared, and omega n squared zeta squared. They will cancel each other out. And we are left with omega n squared. So we have to take the square root, therefore the absolute value is equal to omega n itself. Now, we can also, so the absolute value of the solution is omega n. Now, we can also look for the angle. Therefore, we need the atan of this. And the way that we, let's call it angle, the atan of the imaginary part divided by the atan of that divided by the real part. So you can also see that this ratio has omega n in its numerator, omega n in its denominator, so we can get rid of that. So then it looks like this. Now, if you actually think about this, you'll see that this is a triangular equation, and you can actually see that this is the cosine of the angle between 1 minus zeta squared square root and zeta. But for that we need visualization, but you can see, or what we should at least conclude from this, is that the angle in the phasor form, or in polar coordinates, the angle relates to zeta, and the absolute value relates to omega n. So that's basically it. Now, we also have this omega n squared in order to have a gain of 1 if you use the final value theorem on this transfer function. Applying a step input, you'll see that plugging s equals 0 or s tending to 0 will give you omega n squared divided by omega n squared, which is equal to 1. So this is an ideal transfer function that we think about if we are talking about second order transfer functions. Yeah. There's also this nice thing that we know the settling time of underdamped second order transfer functions. Now the overdamped and critically damped transfer functions are most of the time not even considered because we don't really know the settling time of them. But we are interested in underdamped solutions because most of the time we will have overshoot. These don't have overshoot, so that's that. We know that the settling time of such systems are approximately, again, equal to zeta times omega n. Now this is also aligned with the fact that we can just use first order systems and say that 3.91 or 4 divided by the pole gives us the settling time. Since our system was had real poles, we could just take the real part, which is p itself, and 4 divided by that gives us the settling time. Here, keep in mind that zeta times omega n is actually the real part of our solution. So we take the real part of this complex conjugate pair, and 4 divided by that real part gives us the settling time. So there's still some similarities with the first order systems, but we have to take into account that we have zeta and omega n, but their multiplication should be a certain value if we are aiming for a certain settling time value. So that's that. Therefore, if we want to set the settling time equal to 4, for example, zeta times omega n should be equal to 1. That's one info that we gathered now. But yeah, if we have a second order system, this settling time will be useful. But if we have a higher order system, then we are in trouble, actually. But no problem, we'll talk about that. So, since we have only the limitation of settling time, we can just directly try to pick a settling time for this system. Now, usually we would start with an overshoot value and a settling time value. Then, since the overshoot itself is zeta related and the settling time has zeta and omega n, we have two actually identities for two unknowns. Therefore, we would just directly calculate a corresponding second order system. So this means that in order to be able to design controllers, the first step is to think about first order and second order transfer functions and their relation between time domain specifications and poles. Now, zeta and omega n allows us to do that because we can talk about zeta, we can talk about zeta times omega n, we can calculate them, and they will translate into poles or even the transfer function itself. So what I mean by that is, let's assume we have an overshoot value, and let's say overshoot is equal to 0, we pick zeta equals 1. At that point, we will just pick a omega n value of 4, so that we, or of 1 in this case, since we want to have 4 seconds of settling time. So zeta is 1, omega n is 1, all is well at this point. Now, if we have zeta 1, omega n 1, you can just directly plug it into this definition. You will see that it will be 1 divided by s squared plus 2s plus 1. And that's basically it. You should aim for this transfer function if you want to have this settling time and overshoot values. So that's basically the thing that we are trying to do. Now, in case of higher order systems, we have no tools for that, but we have something called dominant pole placement, which we can use. So we are hoping for, since we have 3 poles, we are hoping for the following scenario. If you have 2 poles that are picked based on settling time and overshoot, and if we have a third pole, let's say times p divided by s plus p, let's say we have this transfer function. So this is a third order transfer function. It has 3 poles. Now the thing here is that this part should be chosen based on the settling time and overshoot values, and this part here, if the p-value, or if the third pole is far away from these 2 poles, then we hope that it will work. So this is basically our strategy. This is going to be our strategy. And let's see if it's really the case, if we can do such a thing. Let's talk about that and let's see. Now I'm going to get rid of everything here. We know that the settling time should be equal to 4, and we have no further information at all. So we don't know what the overshoot should be. So first of all, I need to define the same system in the symbolic toolbox, or using the symbolic toolbox, which is 1 divided by s times s plus 5 times s plus 8. So that should be it. Now, we will have zeta and omega n values. We still don't know what they are. And then we will also have this part here. So let me just comment it out. Now, at the moment, I know that I'm going to design a p-type controller. So I'm defining my coefficient. And due to the connection, due to the unit feedback connection and my gain, I know that I can calculate the closed loop transfer function using k times GSS divided by 1 plus k times GSS. And I can also decompose it into numerator and denominator, numdan. There we go. Let's look at the denominator. Now, this is our characteristic polynomial, and yeah, we want to end up in 2 poles that should have zeta times omega n equals to 1, and everything else we don't really care about that. So if I'm going to design a controller, or if I'm going to pick poles, what I do is I know that due to settling time we have 4 divided by zeta times omega n. So what I can do here is I can just use the following identity, or using the formula in this form, Ts times omega n. So it is basically the same, but I have replaced Ts with zeta here, so I've changed their places. So that I kind of assume that zeta is in terms of omega n, and if I plug in this zeta, or use this zeta value here, let's get rid of zeta here. Here zeta will vanish and this will be a polynomial in terms of omega n. So let's call it PDS. PDS in terms of naming scheme is actually the desired poles or polynomial. So this is our desired polynomial, but yeah, I cannot really use a second order polynomial and equate it to a third order one. What I can do is I can add just one pole to it, sims p, let's call it real. It should be real because we have a complex pair already here, and this is the third one, and it should be real. And let's call it PES in terms of residue polynomial, and that should be s plus p, and the whole multiplication should be PDS times PES in order to match the order. So let's see. One more. Okay, it complains about TS because we didn't define it. Let's go up here and let's say TS should be equal to 4. There we go. Of course, it's not directly obvious that we have a coefficient by coefficient, or if we can just equate the coefficients of these two polynomials, because if they have the same coefficients, then they will have the same poles. Now, therefore, we need to find the coefficients of this polynomial, the coefficients of this polynomial, equate them to each other, and hope that we can solve the set of equations that will arise. Now, we can maybe do an expand on this in order to see if they will align. Not sure if it's going to work, but let's try it out. Yeah, it did kind of, but the order is inverse. So we have s cubed, so this is also s cubed, nice, they should be equal to each other. Then we have s squared term here and an s squared term here, so 2 plus p times s squared should be actually equal to 13. So we can see that we are actually limited here. The 2 plus p should be 13, so p is going to be 11. And the s terms should add up to 40, so 2p, so this makes 22, and then plus omega n squared, so 40 minus 22 gives us 18, and square root of 18 should be omega n. So we know what p is, we know what omega n is. At that point, the last term, p times omega n squared, which is basically 18 times 11, should give us the k value that we are looking for. Now you can see that for this specific type of problem, we have actually a solution. And the reason for that is the following. Since the closed loop or the open loop transfer function is a third order polynomial, has a third order characteristic polynomial, what happens is that we should equate that to something, but we have basically the s squared term, the s term, and the constant term. So there are 3 coefficients, and 2 of them are known. So if we equate it to something, we don't know what omega n should be, we don't know what p should be, but still we know what zeta times omega n is. Therefore, there are only 3 unknowns, k, omega n, and p, and equating these two polynomials gives us 3 equations. So 3 unknowns, 3 equations, we can solve that. So that's kind of the mentality here. If we want to decide on the third pole, it's not possible. We should get rid of the setting time maybe, that could be a thing. So we cannot have everything at once, but we can maybe hope that this is a good solution. So let's actually solve it. Instead of doing it like this, we're going to define the problem. It'll be the coefficients of the denominator, all the s coefficients, equals to the coefficients of the polynomial that we have constructed, basically. So if you remember, I've talked about the coefs function, and I said that it is important to have a certain ordering, and it is important to stick to it. And this is the reason why. If we mix up the ordering, it could be the case where the s cubed term or coefficient 1 is equal to k, and then 40 is equal to the s squared term of this polynomial. So it would mess up stuff, or if there's a missing term, then it will just not even be possible to solve it. So having a certain protocol here and sticking to it is quite important in this case. Now there could be a case where s cubed or one of the polynomials have a coefficient for the s cubed term, and the other might not have that. So in that case, we should just normalize it. So dividing the whole polynomial into its highest order coefficients doesn't change the position of the poles. So therefore, we can just turn it into a monomial, and its coefficient should be the highest order power coefficient should be equal to 1. And if it's not, we can just get rid of the coefficient by dividing the whole polynomial into it. But in cases where the first two coefficients are fixed, and we have also fixed first two coefficients for our polynomial here, maybe, and they are not equal to each other, then we cannot do anything about that. So there's no solution that looks like that. We're basically modeling a polynomial, equating it to the actual polynomial, and hope that it is possible to model it like that. So we could have also came up with maybe 2 or 3 poles, multiply them and try to equate them to this, but that would not be possible. So for example, let's take the coefs of s plus 1 cubed, because these are 3 poles that might be a choice for us. You can see that the s cubed term should be equal to 1. We satisfy that. So let me bring up this one here, or so you can see that the s cubed term is equal to 1, no problem. But then the s squared term is equal to 3, and this is 13. So this already tells us that it is not possible to equate these polynomials to each other. It is not possible to come up with a solution where k is chosen and all the poles are at -1. This is not possible. You can also see that 3 is not equal to 40, and at that point you already messed up. You cannot take k equals 1 because it will not result in this. So in some sense, the coefficients should be aligned with each other in order to be able to have solutions or use this method. By the way, the method is called algebraic method because we're using algebra. So it's quite obvious. And the other method is basically the Rootlookus method, which we will use when we have the Designed controller. So enough with the talk, let's solve it. We can use solve on this and say prob and see what the solution looks like. So there we go, we have 2 solutions. Sol.k is 198, we have already calculated that. Sol.p is equal to 11 for both cases, we have already calculated that. And the reason why we have 2 solutions instead of 1 is basically we are using omega n squared, and MATLAB gives us the negative and positive solution, but by definition the negative omega n value is not usable or useful for us. It violates the definition of omega n because it's natural frequency. Frequency cannot be negative. So therefore we will eliminate the first solution, which is not really that big of a deal. We can see that the k value is 198, the p value is 11, and 3 times the square root of 2, which is basically square root 18, which I have calculated on the fly. So we have the exact same solution. Now, let's pick kval double sol.k. Let's repeat this for all the unknowns. Since I need k, omega n, and p in order to use it for subs or for some other, I'm just creating a placeholder for the value instead of the symbolic expression or variable itself. So omega n val and p val. Omega n. There we go. Now we can do the following. We can just say, okay, I want to eliminate some. So k val should be equal to k val. Omega n val should be greater than 0. If I do this to all of them, so omega n val, p val, I'm going to show you in a minute what it actually does. Omega n val. So let me just comment this out, take this, run it, omega n val, solution dot omega n. You can see that omega n val being positive gives me a logical array, so it means that it checks individually, and this one does not satisfy it, obviously. This one does satisfy it, and I can use this 0, 1 in order to eliminate the unnecessary ones. Omega n val greater than 0. You can see that it directly gets rid of the negative one, and it gives me the positive one, which is square root of 18. There we go. Therefore, I'm eliminating them. But keep in mind that I am using omega n val for the condition. In order to be safe, I have to eliminate omega n val at the end of these operations. Because if not, if I change the ordering here, you'll see it'll crash, or it will not eliminate it. So omega n val seems like that. K val seems like that. For some reason here it does not really break the code. But this is not a good thing because we're eliminating that. In order to be safe, there are two possible ways of doing it. One of them is to save the solutions which are important, the indices at least, and get rid of this mess and just take the indices here, or eliminate omega n at the end, not at the beginning or anywhere else, just at the end. So let's do it like this. Let's check for indices which satisfy omega n val being positive. So we have basically our solution. At this point, we can leave the symbolic toolbox or the symbolic domain, and we can just directly check for the solution if it's going to work or if it's not going to work, or what it really looks like, what the closed loop really looks like, what the step response really looks like. So therefore, I'm going to define my controller that is equal to kval, and that's basically it. I'm going to use the feedback command, which is in the transfer function, which uses transfer functions, which is in the control system toolbox. So fs times gs, comma 1 will generate me the closed loop. So I can use for ZPK, I can look for ZPK, I can look for the step response, PZMap, whatever I want. So yeah, let's run it. Now I can see first of all that we have a second order polynomial, and we have s squared plus 2s plus 18. So it makes sense if omega n is square root of 18, then omega n squared is 18. So this was s squared plus 2 times zeta omega n, and the multiplication zeta omega n was equal to 1. Therefore, s squared plus 2s plus 18 should have been expected already. So that's not that big of a deal. And we have also s plus 11 and p-val, or the value of p was 11. And the value of k was 198. You can see that the values come up in the closed loop transfer function itself, which is quite neat. Now, you can see that the real part of the solution is equal to 1, and we have 11 here. So it means that one is here somewhere, and the other one is far away on the left. So this will be hopefully a good thing. So I don't really know why yeah, there we go. So we can also look at the step response, but let's do it a little bit more visually. Let's enhance the visuals here. Let's have a subplot of 1 by 2, 1 row, 2 columns. The first one of that is going to be this one here. Let's open up hold on, grid on. I'm going to write this code over and over again, so you might want to get used to it, and it'll come up all the time. So don't be scared if you are not really familiar with this. I'm just setting up some visuals. So I'm going to have a step response plot here, and I'm going to reuse this code, so I'm kind of rushing it now. Let's also give it a color. So there we go. Now PZMap can give me the poles and the zeros, so I'm going to create another, or use the second subplot, the real axis, the imaginary axis. Title is going to be pole 0 map. Now I have acquired that. Let's plot them. Real of C poles, imaginary of C poles. Use some markers, increase the line width. Repeat it for the zeros, or even omit them because we don't have any zeros. Yeah, seems to be the thing now. So let's run it. Now you can see that we kind of have our solution here. We have a pole pair here with real value 1, and 4 divided by the real value of this pole pair gives us the settling time, which is 4. And we have 11 for the third pole. So we're trying to tell, or we're trying to do the following. We are trying to have the pole pair near the origin, and have the third pole or all the other poles far away, placed on the left half plane. And the assumption is that this pole will not affect the pole pair or the overall response that much, which we will verify and see in the next lesson, by the way. So bear with me. If you don't really get the idea here, we will examine it in the upcoming lesson. And we see that it takes almost 4 seconds to reach this point, which is around 1, and it will wiggle around this kind of value, but not that much, so we kind of are satisfied with 2%. So this is the point where the setting time is almost equal to 4. We can, by the way, acquire this data. We can use info, let's do it somewhere here, info equals step info. It will directly give us the information that we're looking for. And maybe instead of writing a boring title, what we can do is we can just say what is the settling time. So info.settling time, like that, I guess. And then overshoot string info dot overshoot, and yeah, that should do it. By the way, since we have a system, since we are looking for a p-type controller, in the previous lesson we have talked about the root locus plot, and that we can use the root locus plot in order to choose a certain controller, or a certain p-type controller. So what I also can do is I can do the following. Underneath these poles, I can plot the root locus plot and plot these poles on top of that in order to see what is really going on and if it's really aligned with the fact that a root locus plot determines the position of the poles with changing coefficients k. So in order to do that, I can just call the root locus plot of GS. Since I have enabled hold on, it will not be that big of a deal. Let me get rid of the grid on for a second. And let's see what's going to happen here. So there we go. You can see, in fact, our poles are on on the root locus plot. Maybe I should increase the line width to 4. Is it going to be too much? I don't know. Let's see. So that looks a little bit weird, but yeah, for the sake of readability, I think we can get away with it. So we can see that in the open loop we had a pole at the origin, a pole at -5, and another one at -8. So the one at -8 moved to the left to -11, and these two met each other at this point, and they turned into complex conjugate pairs, and we ended up in here. By the way, what we can do is we can, since we know what the omega n value is, so we have omega n value, and since we know that zeta times omega n should be equal to 4 divided by Ts in this case, because of the formula, what we can do is we can use this equation in order to calculate the zeta value and see what really is going on. So once we have that, zeta value here should be equal to 4 divided by Ts times omega n value. So, and instead of grid using here, I can also go a bit further and use this sgrid function. So let me show you what sgrid means. Of course it is a grid, but since we are using it in the S-domain, what you can do is you can use sgrid in the S-plane. So it will show you the zeta and omega n grid, sort of. So these zeta and omega n lines, and it will become relevant in the next lesson. So therefore, bear with me, we will talk about this in the next lesson. So if we provide the zeta value as the first argument, omega n value as the second argument, use the sgrid function, it will plot us the following. So I know what zeta val is, directly give it to the function, and omega n val is also calculated, so provide that too. So now we can see, hopefully that you can also see, let me zoom in a little bit. So we can see the 4.24 is kind of a half circle here, and the zeta is just a plain line with the zeta value 0.23, approximately 0.236. And yeah, let's look at the a cosine, the inverse cosine of zeta val, maybe in degrees, so a cos d maybe. It gives us 76 degrees, which is, by the way, the angle of this line. If you see the line, this is the zeta line here. So the angle here is 76 degrees. So if you take the cosine of the angle, since the angle was related with the cosine, I've talked about this where I was talking about the second order polynomial stuff here, like that. So if you take the cosine of the angle, it will give you basically zeta, the zeta value itself. And we can see that there's a circle omega n, because if you have a fixed omega n value, you will have basically fixed, you will fix the absolute value, and fixing the absolute value here, x squared plus y squared square root is fixed, so you will get a circle. So omega n lines are basically circles, the natural frequency circle, so that's basically one part of the S-grid. And then we will have zeta lines with a certain angle assigned to it or fixed, so that will, and the point that is generated by the intersection of these two lines will give us basically our pole pair. Now, yeah, this is the way of solving it, and if you click on the root locus, I believe it's still clickable here, and if you drag it approximately to this point, it should be somewhere around here, but I'm not really good in choosing it. Let's zoom in a little bit. Let's take this here somewhere. you can see I cannot directly click it. I have to just increase the k vector grid in order to be able to click this. So you have to manually provide the R locus with a gain value or a gain vector in order to meet this point. But it is approximately around 198. You can force it to be like that, and you will see that it will give us the same damping here. So this damping here is the zeta value itself. You will get the frequency value, which is again the same frequency here. So if you're looking at frequency, it is the omega n value. If you are looking at the damping, it will give us the zeta value. And in the upcoming weeks, we will learn how to also calculate the overshoot based on the zeta value or vice versa. And we can directly conclude that the pole is looking like this. We can just directly calculate it. Zeta times omega n will be the real part, and 1 minus zeta squared, the square root of that times omega n will give us the imaginary part. So we can basically calculate everything that is available in this little box here by clicking on the root locus. So I've basically shown you the basic way of using the algebraic method in order to obtain a controller, and you can do it also for the root locus. You can just use the root locus, click on it, and acquire the data. But the algebraic method is basically giving us better numerical results, and we can also see some different things about the design. For example, the third pole, the pole pair, is available to us. Therefore, we can go to the zeta value, omega n value. We can calculate almost everything about the closed loop or the system overall. So, this is one of the designs. So, yeah, and we have also a different settling time. But if you look close, you can see that one of them is just critically damped, and all the other ones are basically depending on the settling time. So what we can do is we can use this code, or this piece of code here, in order to just get the solutions and plot them on top of each other. So the other one is going to be 2.5. What I'm going to do is I'm just going to take this here and put it somewhere around here and make ax1 equals GCA. So I'm going to take the handles, and you'll see why in a minute. So let's take this one too. Let's call it ax2 equals GCA, and settling time is 4, and run everything here, no problem. So once I'm plotting on ax1 and on ax2. Now the zeta values are not really that relevant at this point. I'm not going to bother with that. So we should be good to go. Instead of doing this, let's change it a little bit. Let's do it on the plot itself. We can use the display name property to assign names to our plots. Let's assign this name, and let's get rid of the step response part, because obviously it's step response. So yeah. We might also do it for this one here, maybe, or maybe not. Yeah, just don't. Okay, now let's say legend show in order to show the names of the plots. Yeah, that should be it. Let's take this part up here. I'm rearranging the code so it's going to be easier to reuse. Basically, that's all I'm trying to do here. So that's just going to be plotted once. Maybe I'm just going to plot it here on the second plot, and don't repeat it ever again. So let's say Q1. Yeah, that should be it, I guess. So let's close everything, clear, CLC, run it. It should generate the same results, hopefully. There we go. Yeah, and we have also the statistics here. Pretty nice. So let's copy this part here and paste it here. Call it Q2, and the second settling time is 2.5. So you can also basically write a function that does this, but I'm just going to simplify it for you because I'm trying to make a point instead of program it in a certain way. So let's assign a blue color to this, so everything that I'm going to plot here will be blue, so I can distinguish them. And yeah, let's see. Let's run it again. One more time maybe. And you can see we have the solution. Now, the settling time 4 divided by the settling time actually gives us 1.6, which means that we are choosing a solution that is more to the left. And why do I know that? Because the line that goes through both of these poles here, or the pole pair, the real value of that should be equal to 1. So 4 divided by 1 gives me the settling time 4. If I decrease this settling time, I have to increase this value, because 4 divided by what was it again? 2.5 gives us basically 1.6, and 1.6 is more to the left. And if it's more to the left, on this root locus, I can see it will have a lower gain value. So the k-val here is 84, where it was 198. So it's a lower k-value. It's earlier on the root locus, and I can see that the p-value here is also a lower value. But since the angle of the zeta value, let's see what zeta value became, it's 0.5. The a cos d of zeta val gives us a lower value. It was 76 degrees, I guess. Now it's 57, so it's a lower value here, so lower degree. And increasing the zeta value, it was 0.23, it's now 0.54. So higher the zeta value, lower the overshoot. And we can see that the oscillations drop down. It is a lower overshoot. It should be around the same settling time, hopefully. It is actually 2.5. We have 2.08. We can live with that because now this pole is closer to this pole pair. So if it's closer, the setting time value will be less reliable, because it is just modeling the settling time of this pole pair. They should be alone, but they're not. A third pole approaches them, so therefore the settling time formula is not really correct, because we have a third order system, not a second order system. The same goes for actually the black ones here, but since it is 10 times far away or further away, so we have a better result. It is almost 4 seconds, so not that big of a deal. 3.95 is quite close to 4, so it works if it's 10 times away. But if it's becoming closer, and we can see how close they became, ZPK TS, so you can see it is 1.6 and 9.8. So 9.8 divided by 1.6 gives us the dominance factor of 6.12, whereas we had 11 basically, because it was s squared plus 2s and s plus 11, so the dominance factor is 11. So twice the dominance factor, better the result, but half the dominance factor, it has more effect. But it's still there, because 2.5 was the original settling time that we were interested in, and we got something around 2. So it's still okay to us to have this close, because we have no other methods. We cannot come up with a settling time formula, or we don't have any settling time formula that gives us directly a relation between the poles or between 3 poles and the settling time. The best we have is a second order polynomial, or 2 poles or complex pole pair even, and a settling time, and we can assume that this should be far away and it will work. So that's what we got at this point. So let's actually continue. Now, instead of having a certain settling time, we directly have the zeta value itself. So this will change the code a little bit. Therefore, let's copy Q2 now, and now instead of having the settling time, we have actually the zeta value itself. Let's assign that. Zeta is equal to 1. We will be interested in s squared plus 2 omega n s plus omega n squared, which is obviously omega n, so the poles are omega n. But yeah. Now, since we are considering the zeta value like that, zeta is already equal to 1, so we don't really have to calculate that. Omega n val equals this. So do we have any other issue? We'll see. Let's first of all solve it before we plot it. So let me assign another color to it, maybe red. And let's solve it. So k-val. Now we have again multiple values, p-val. Now we see that there are two solutions. If we look at the solution, we have two solutions, but one of them has a negative p-value. So having a negative p-value means that we will have a right half-plane pole, or an unstable pole. And if the overall closed loop system is not stable, then we can not really use that controller. And it is also a negative k value, by the way. So it means that we have to check if p-val is positive and eliminate the other possibilities. So let's do that actually. Our code needs refining. So maybe we can use the AND operation and say p-val needs to be positive. So what happens if I do this? So maybe just one AND in order to AND them individually. Seems to be the case. So omega n val, p-val, k-val. So we've eliminated basically the negative ones. So now we can plot them, I guess. Run it one more time. There we go. Now, we can see that we are looking exactly at the point where they are on top of each other, which was expected. And it happens even earlier. So the k value now drops down to 36. It was 80 something. Now it is 36. It happens earlier because the root locus shows us that. And therefore, the pole gets even closer to the pole pair. At this point, we are not really going to be that happy about the settling time, because the settling time formula itself, it doesn't even correspond to zeta equals 1, or doesn't work for zeta equals 1. The system has to be underdamped to us to be able to use that settling time formula. But yeah, this is all that we can do. Therefore, we will be using it basically. So yeah, what is the p-value? It is 9. It is becoming closer and closer, but it still works, and our data here shows that there's no overshoot because it's critically damped, and the settling time value is around 3 seconds. So it's a higher settling time than here, but yeah, still that's only what we can use here. So now we have actually completed the first 3 tasks here. We have set the settling time to 4, we have set the settling time to 2.5, and we've also tried the critical damped solution. And all we did was construct just one way of solving it, and we've refined our code basically. It didn't take that much. We were looking for a desired polynomial. If we have a certain settling time, we know the zeta times omega n multiplication. If we have critical damped, we directly know what zeta is, but it doesn't really change the type of code that we have to write. In fact, I've just copied and pasted it. But we did add a certain thing to it. Well, specifically for this problem, we can get away with this code, but actually p-val should be positive. K-val can be negative. It's not really that big of a deal, but we would like to have it positive. And of course, omega n val should also be positive. We have to check all of these in order to get the actual solution, but we saw that this was already positive. We didn't add it, but you can go ahead and add this piece of code there, so you have a safer code basically. Now here for Q4, what we are going to do is we are just going to copy it. Before we verify it, we should solve it. Well, actually I should copy Q1 maybe, or Q2, because we had a settling time there. So let me copy this, let me paste it here, call it Q4. Now here the settling time is requested to be equal to 1.5. So let's try that. And let's get rid of this part here and let's solve it. Now it is interesting because the setup is interesting here. We have a settling time value, another settling time value, critical damped, and then again settling time value. Let's see what it is going to show us. Run it again. So let's look at our problem here, or solution even. So what is k-val? We have an empty k-val, empty p-val, so solution, it didn't come up with a solution. So it couldn't solve it, by the way. So zeta val, it's just empty double row vector, everything is empty. We couldn't solve it. So yeah, how can we identify the problem? Because we don't really have a solution here. This might happen. We don't guarantee that we have a solution. So what we can do is actually we can look at the problem itself and what we are trying to accomplish here. Now 1 equals 1 is the first equation, which is not really that important. We should have a p-value here because 13 minus, let's see, 13 minus 16 divided by 3 gives us 7.667. So p is around this. And yeah, we have this equation here. Now 16 times the answer, 16 times ans divided by 3. This would be this part here. It gives us 40.888. And this part here is 40. Now, if we want to satisfy this equation, it seems like omega n squared should be equal to minus 0.889. And, well, this is not really possible. Omega n should be a real value, by definition, and positive. If we solve this, we will get a complex number here. Now, in order to be able to solve this, what I can do is I can solve it. If I get rid of this real definition in line 139, it should probably give me the solution. But, of course, if I'm going to be able to use it is another question. But still, I'll get the solution. I can see what sol.k is, sol.p is, sol.omega n is, and I can see omega n is actually not a real value. So, interesting. And it is interesting for the fact that the k values are only negative. So this point doesn't exist on the positive root locus at all. So in order to see what really is going on, I might go ahead and create another figure just for this and try to plot that point. So hold on and R locus, but the negative R locus, so minus GS. And since, yeah, do we have kval? We have kval, but it's not assigned, so why is that? Oh, this elimination. Let's get rid of that. Let's just get these. And maybe we can look for kval here. So kval will be important. Minus 6. I'm going to use that value in a minute. So we have the negative root locus here. And what happens if we have the k value here? So let us create TS2, something like that. Use the feedback. Since I know what the k value is supposed to look like, I can just use that k value, just one of them, gs, comma 1, and get the poles, pz map, and draw that on top of the plot, the root locus plot here. So let me just copy this part here. So let me copy this. There we go. No AX2F whatsoever. There's hold on, no problem. Let's call it magenta. There we go. There we go. Now we see that, even though that's the case, have we pval, we have pval, which is approximately 7. We can see that, first of all, if we use zeta and omega n as a definition, we will have, based on the zeta value itself, we will have a complex pole pair. But in this case, it seems like we don't really have that. We don't have an underdamped solution, and therefore there is no real value of the complex pair. And 4 divided by the real value of the complex pair, which is zeta times omega n, is not really usable here. We are looking for a complex pair, and it should be on a certain line, on the settling time line exactly, but it's not happening. And even further, we have another problem. We have a right half plane pole. So one of the poles goes to the right half plane. Now, what is the value of this? This is probably pval. So let's actually plot pval 1 minus pval 1, comma 0, and then maybe a square with line width 4 in order to visualize that. So we can see pval is the leftmost one, so it is this one here, pval, but the zeta omega n pair, they just are not there. One of them passed to the right half plane, the other one is on the left somewhere, but they should be a complex pair, so we have a real value that would correspond to the real value that is necessary for the settling time. And to top it, we also have a right half plane pole. So yeah, we can see that this doesn't really correspond to a solution that we can use. Basically, zeta is greater than 1 at this point. Do we have a, since we don't have omega n value, we cannot really have a zeta value in this case. Yeah, therefore we don't have the luck here, but 1 is passing to the right half plane, and they are not a complex pole pair, so this is not a valid zeta omega n pair that we can use. Therefore, we cannot assign the settling time of this system to 1.5. It's just not possible. And in terms of the problem, we can see that yeah, omega n cannot be a real value. If we look close here, omega n squared needs to be negative. That's not possible. So therefore, we cannot use this setting time value. So the p-type controller is not able to assign the setting time value to 1.5, but other than that, the other setting time values did work, and we did see that the results are here. It is possible to use 2 seconds, 3 point something, or even 4 seconds as a settling time for this system. But other than that, we can see it's not possible. Now, you can also see on the root locus plot that the gain value was negative. Now, for positive values, we don't get even a complex pair. So the point where we had the critical damped solution was actually the limit, because then one of them gets slower and slower and the other one is just getting faster, or they move to the right and to the left, and at some point one of them is at this point and one of them has crossed the j omega axis. It is on the right half plane. It's not a stable solution anymore, so therefore we are not able to use it. And even worse, the other one, the p-val, is even getting more closer, so that was also not a good idea. If we want to control this system, and if we want to have a certain setting time, and we are okay with overshoot, it seems like we have to use higher gain values or higher k values, and that would correspond to a slower and more damped or more overshooted system or oscillatory system. So it seems like the blue one here and the red one here can be good choices. So choosing the settling time like 2-3 seconds is ideal for a system, but having slower settling time values or higher values for the settling time and slower closed loop systems does not really make sense for this system. Overshoot increases, settling time increases. What good is this system? And it's also not able to force the system to be faster than the red one here, because we see that it's not really possible. Right half plane crossing happens, or instability occurs at that point. So we should be sticking to the blue one or red one, or in between is a good choice for this closed loop system using a p-type controller. But we can see that we are not able to place the poles arbitrarily because, well, we have some limitations on the coefficients. Some of them are already fixed to some values, and others might have restrictions based on the positivity of omega n. So, in short, we are limited to the root locus plot here. So if we increase the k value, we see that zeta will decrease, so overshoot will increase. If we decrease it, we will have 3 real poles maybe. That is also maybe problematic. We need to look numerically what the settling time value should be, but then we will have no overshoot. So it has its pros and cons, but we are limited to the root locus plot. You could also maybe look for the negative root locus plot, but at that point, since we have a pole at the origin, the negative root locus is never an option at all for this system because it's not stable, first of all. So p-val, or the third pole, should be on the left half plane. The zeta omega n pair should form a complex conjugate pair in order to be able to use the settling time and overshoot in order to assign these to the closed loop using a p-type controller. So that's it for this week. Hope that this introduction of p-type controller, the algebraic methods, and some of the zeta omega n part did help you out. Next week or next lesson, we will be focusing on zeta and omega n and the effect of the third pole maybe a little bit. And after that, we will get more involved into the controller design. We will dive deeper into this topic. So this is it for this week. See you in the next lesson.